So welcome back. We are very happy to have Mandy Cheung tell us about some examples of family floor mirror.
Thank you very much for Helter's introduction, and thank you very much for inviting me in this for theory conference, which I'm trying to learn the material, and I believe they're expert in this area than me. This is kind of a continuation of today's morning talk. The two morning or afternoon talks today are about the canonical scattering diagram, and then what both we mentioned about is kind of constructing the mirror in this algebra geometric way. So today in this talk, we'll just kind of explicitly do it we just turn everything you see in the morning today, like scattering diagram, theta function, all the things with a synthetic meaning, and then we interpret the construction as a family floor mirror. And this is a joint work with Yushen Lin. It might be here or not. As the structure of today's the conference, we are having two parts. The first part is elementary, and the second part will be about my result. So when I was preparing, I'm thinking maybe we can just do the first part is the introduction of cluster varieties, which at the end you can see I can kind of skip cluster in this project, but you can also see from my point of view, cluster variety give me all the motivation of how all this construction work. So the first part will be just a very brief introduction to cluster variety. And as we are example, we are still in the JHK world. We haven't get to the high dimension world yet. So today's talk will be just 1, 2. And cluster varieties are log real varieties, which can be described as a union of torus, where the torus are just 2 dimensions. And then here we have the transition map. Something because we are doing cluster theory. So the transition map are just composing something we call mutation. But if you are not a cluster people, birational geometry people, that will be just some birational map. As this talk is entirely example based, so I'm not going to give you a full definition, but just one example, which actually appear in both Mark and Julia's talk and in the computation of wall crossing already, which we have XY map. If you remember in Mark's calculation of scattering diagram, he has X map to X as some wall, Y times 1 per 6. So it is 1 per 6, something like that. This is one of the example of our mutation map. And then here is we have the gluing of the torus. And then in the cluster theory, in this work by Gross-Hawking Q consideration, this gluing can be combinatorically described by the object mentioned in the first 2 talk of today already, which is a scattering diagram. And there are a lot of discussion of scattering diagram in the first 2 talk already. So again, I'll be rough. Scattering diagram is a collection of walls with some conjunct, finite up to finite order and consistency. We have in the second talk today. And the condition of consistency we are going to see is actually ensure that, maybe I should write a bit here, consistency, ensure that the gluing of torus is well defined. Like from this now in this cluster perspective. But then what is a wall? Then it is like the first part of Julia's talk, because it's dimension 2. A wall dimension 2 will be a ray or half a line with endpoint from the origin and with a rational slope v, and a wall function just some polynomial or power series dictated by this slope maybe with a plus or minus there, depending on which sign convention you choose. And we're going to repeat that, but as it appeared in the first two talk already, you can see this number here are coming from some gamma written curve counting. And then again, as this talk is example case, so we have two scattering diagram. The first one appear in the second talk of today already. So it is this one. And then we compute that this extra line is necessary to make the scattering diagram to be consistent. So this is a consistent scattering diagram. In the cluster theory, we call it type A2. And then we do more than just one example, that from A, we move to B. So what we are doing is 1 plus x1 squared, 1 plus x2. And then what the consistent scattering diagram will be this thing. We have 1 plus x1 squared x2 and 1 plus x1 x2 squared. And then this is what we call type B2 in the cluster world. This will be the two example we are having in this talk of today on in the collaboration with Lucian. So here, when in the beginning, like we are in this talk, we are not doing curve counting. I'm telling you that like scattering diagram from up to this minute is telling me how to construct a cluster variety, how to do the gluing. So how do I do that? Which is I have this scattering diagram there, which is, let's say A2. I can go back to this one. What I do is I just associate a torus to the maximal cone, or we can just call it chamber. And from the calculation that Mark was showing us in the Q&A of the last talk, we have this calculation for wall crossing, and you can see this is basically doing the function here. So to glue the torus, we are basically doing the wall crossing. So you can see this is a way we do. Actually, you can see I will keep on repeating this picture again and again more than 3 times in today's talk, which is we associate torus to a chamber, and then the function associated to the wall is, to me, is how to glue between the torus. So here is it. And so here I kind of hide away some formality that when I was doing a way I say is this R2. So when I was writing the slide, maybe we slightly being formal. What we are actually doing is we start with a lattice of the two, and then we have the dual torus, the two dual lattice. In the case of B2 in the cluster world, we are actually having some scaling of we are working with some scaling of the dual lattice. Have M, because you can see we have a 2 there. And then but then here, for simplicity, let's skip the definition. And then we have NR is 10 and tensor R, and MR is MR, like tensor R. And now scattering diagram, you can see I just make correction. We can either lie inside actually we can either lie inside MR or NR, but in my example, I'm actually lying in MR. And so the next thing, the reason I was telling about the lattice point is a hint in Julia's talk that she mentioned. For each point in the lattice, we associate a theta function to each lattice, which is the global function of our cluster variety. Yeah, it begins in U is the union of torus. So those are the global function of my cluster variety. In Julia's talk, she was telling us that we can define it by Bokenai. That is a very general, that is defined for very general setting. But today we are only working with finite case. So actually you can basically see theta function. I have a toric monomial in this torus there, and then the wall crossing are just telling me the change of variable by the Goulding in this finite case. And then what we consider is we consider the space that is generated by the theta function. And then what GHKK show is this space is an algebra that very equal structure. And this is GHKK result. And then if you are in the cluster world, that is the cluster algebra, middle cluster algebra. But if you don't care cluster, this is simply the algebra that gives the global function of the cluster variety. And the very first example is example 0 or example 1, which I just consider torus. I'm not going anything. And as in Julier's and talk, you can see actually what I'm thinking behind is I have a log Calabi-Yau pair, which I take P2 minus C0, C1, C2, the zero locus of C0, C1, C2. And then the global function of the torus in toric geometry can be expressed by characters AI in C, which you can see I can even write in A or N in M, C set M, and those are our global function without Goulding. And you can see this is the very easy way, like example for what our theta function is, or just toric monomial in this example. But like you can see, I just finished first half of my talk. The reason is usually when I tell people cluster variety are going off torus, my feeling is both geometry are very upset about it. So let me give you another description. Cluster variety, which are just go up of toric variety, which Julia have roughly touched that part in her talk. She mentioned about Toric model, which is we are having this. This is the Toric model in her talk. That is, we have a blow-up of the Toric model to this pair. And so I'm going to illustrate this idea, repeating the same thing but do it in two ways, but they are almost identically the same. The first thing I want to convince you, this birational map, this mutation map, 1 plus x, 1 plus y is very natural. You can just come out by just brute force computation. And the second thing, I will repeat the same calculation by drawing picture in terms of this Torrent model. Yeah, you can see I'm very happy that in the first two talks, Mark and Julia mentioned about Toric model because I was hesitating if I should define it in this talk. So for the first illustration, let us simplify the story and just talk about A2, the complex C2, and then we are just looking at this divisor x is 0. So we are having this x is 0, y is 0, and then we want to bow up at the point 0, minus 1. So we bow up at 0, minus 1, and then we have the property transform of this bow up of the divisor, which going this way, something like that. And then this bow up, you know, if you flip and chat hash on, or whatever algebraic geometry book will start with, that will start with this C2, the coordinate xy cos P1 st, which have the relation T is x, y plus 1. And this is the from Boab definition. And then here we consider mu tilde x tilde y minus d. And I'm telling you that I have this cover given by 2 torus chart, which this is the first one, this is the second one. And the first one is as simple as, because this is the first 2 are xy there, so I just simply map it to xy. And then from this relation, I got 1 plus y, x in the P1. And then the second one, but I also want to cover the exception curve too. So here I do 1x in P1, and then again we do algebra. From this relation, we can go back and compute this C2. We have this thing. It's simply by this relation and doing the computation. And so now we look at the transition map. Let me see, I'm going this way. So compose I2 inverse, and then it's just as brute force as just computing this 2 map. And you can see I obtain a map like this. So you can see here, this is just the mutation map I set in the very first minute, and here I have this mutation map. It's a directional map between 2 torus, and they are covering this blow-up. It's as simple as blow-up of C2 at one point. So this is the way we do it by brute force computation. And the second way is do it by picture, which I kind of partially compactify it. That, yeah, here I'm looking at this Toric model, which is P1 cross C. And then here I blow up at this point P. Here is a with self-intersection 0, self-intersection -1. Here I still have the P1 there. And then you can see actually what I'm doing this first and second track is I kind of doing inversing on this P1. So what we are thinking is here I got this, I don't know how to change color. Like I got this exceptional curve, and I turn it to here, and then I bow it down. And so I got now this picture here, and then this thing, the torus, and then this process we just compute here are just actually having this mu here. So this is the picture, depending on what favor you are, more algebraic or geometric. But I hope here at least I can give you, even though I'm repeating, but I'm giving you 2 ways to demonstrate how we can think about this mutation map. And here one thing to note is if you really try to do the algebra computation, you can see the union of this T and T prime. It's actually missing out this point W here. Like it covers everything, just not this point W. And then the next example, this is an illustration. The example, as Julia said, the very first example everyone will do is DP5, both of P2 at 4 points, and then the X is 10 -1 curve, which you can read Dr. 12 or the classical algebraic geometry book. They have a dual graph that is dictated by this Peterson graph, because the vertex will be the curve, and then the edge mean they have a intersection. And then here you can see when I was describing this picture of mutation, I have a Toric model. So the first thing is to describe this mutation. I want to look for a Toric model for this for DP5, which I start with this 5 minus the string of 5 minus 1 curve. You can choose it from the Peterson graph. And then let's see, didn't leave space here. Okay, I can draw that. And then from this Peterson graph, you can see once I used to do this change, like every one of them will have one and only one another minus 1 curve going from here, and with chaotic relation coming from this Peterson graph that you can dictate it. But here what I want to do to do the Toric picture is I will bow down 2 of them. I always lost counting 5, so let me make sure I'm correct. 0, 0 here.
Mandy, sorry, I don't know this very well. Like, how did you get the Peterson graph? Maybe I missed it.
That is. Can I say something? It is classical. I learned it from Dongatrov. Like, I don't know. Maybe there's better algebraic geometry here, but to me, it's something that people compute. DP5, we have 10 minus 1 curve, and the relation can be dictated.
Okay. Okay, no worries.
You want to add something?
Comments here on how you can realize that. So if you simply take 6 lines in P2, intersecting each other at 4 points, some configuration like this. Mandy might remember I had actually drawn this at a lot of talks. If you take 6 lines and blow up at 4 points, so in P2, these intersect, every parallel lines intersect. All of these 6 lines turn to -1 curves, and these 4 exceptional curves also turn into -1 curves. So you in total get 10 -1 curves. And just by analyzing the picture, you can get the Peterson graph, which is also explained well in Dolgachev's book.
Yes, thank you. Continue. Sorry.
No, that's very good. Thank you very much. Yeah, really remind me. I should start with P2 and then we bow up, and then this is something that, yeah, you can calculate it. Yeah, no, thank you so much. I was like, oh gosh, this is in the middle, I forgot. But anyway, what I want to say, emphasize here is this is the Toric model in Julio's talk, actually. Actually here you can draw the fan picture and you can already see, actually this is P1 cos P1 blow up at a pawn. So you can actually see the scattering diagram already, sort of. And then here is, but this is my Toric model, and then I want to do the same thing, which I pick a pawn and then bow up. And then here, and then the mutation is I flip to another one and then bow down. So I got -1, and I bow down here, which I got 0, 0. And if you keep on doing this process, you can see you need 5 torus to describe all those relations, like depending on which language you're in. You need all the torus to give all the variable, or you need all the torus to cover the space or to describe the relation between the curves. And actually, if you like, I can perfectly, anyone of you, I can perfectly send you some pictures of how we explicitly do that calculation. But in Julio's talk, she mentioned one thing, which is theta function. In custom algebra world, we call them custom monomial, custom variable. The way to see it in this DP5 is we have this dp5, which is dipixel surface of degree 5. So we have this embedding to p5. The coordinate are, let me tell you already that theta, that is theta function, but let's just say these are the coordinate of the projective space. And then we can choose the coordinate such that our device will be just theta 0 is 0. And I might take it out and look at the affine piece. And here, let me slightly use notation, which I still, in the affine piece, I still call it theta I. And then my consider, you can see my U is x minus d. And then I obtain the relation theta I plus 1 plus 1 plus theta I in C. I think that this relation also appear in Louis' talk, right? I forgot. But you can see there's many ways you can see it. It can depend on which type of people you are. If you are cluster people, you start with here, which we have a cluster variable. We have the exchange relation to generate more variable. You can see here, like I have a torus with X and Y in each torus, and then when I mutate, I got, with the change of variable, I got more variable, and then I got it there. It really depends, but you can see at the end, what we have is, we have this relation between in the space, and then maybe slightly more space than I thought I have. Slightly more space. Oh, anyway, let me erase that. And then here is, yeah, let's say the theta IR cluster variable. And then the terms we are choosing, you can compute and see they are theta I plus 1, not 0. So you can see they are just the torus. I start with saying how our cluster algebra, cluster variety is defined by cluster grouping of torus. Up till here, actually, you can see I use nothing about cluster theory. That's why in the beginning I was saying one can talk about this project without touching about cluster. But as I say, we have two examples in this project. The first one is A2, the second one is B2, which I can compute the cluster variety there, which is just U is just going of torus with this 6 torus. But at least from my understanding, what is the compatification is not very clear, which we can use in the cluster world, the machinery that is proposed or written or constructed by Grosshawking Q consideration, that using a positive polytope to compactify the cluster variety, because you can see here, this is the cluster variety is very affine. And then, but if you want something, like when you read the definition, is everything is written there. But at least from my point of view, it's very hard to check what if a polytope is positive or not. But then with T. McGee and Alfredo, Najjar, Schaffer, we show that combinatorically you can check a polytope is positive or not by something we call Bokenline convex, which Bokenline appear in Holyfield's talk already, which what we're saying about Bokenline convex is given 2 points in the polytope, all the Bokenline that join the two points must contain in the polytope. And with McGee, actually we did the B2 first before Bokenline convexity, but anyway, in this scattering diagram, one can check that a point of light is positive, and then it carries 6 points, so that we can see you carry a compactification to the apical surface of degree 6. I believe there will be other way to see this is dp6 by checking, like Julia said, book of B2, but you can see in the Castor theory, we also have this machinery to look water spaces. And then, let me see. Let's skip anything. No, okay. And then here, sorry, I don't know how to control one. No. Here is you can see the first part of the talk today. I hope I can just convince you to message. The first message is we have scattering diagram, and then we associate torus to a chamber, and the space we obtain at the end are just screwing off those torus, and the combinatorial can be described by scattering diagram. And the second thing I want to say is the global function of the space is given by theta function, which appear in Julia's talk. You can see it's a monomial here. I compute path ordered around or computed by. The main thing is the collection of all those the vector space generated by those global functions is actually carry a algebra structure. And I'm going to tell you in the next talk that the heuristic mirror are just a spec of this algebra. And with Notion, what we are doing is you can see on one hand we have a space X, XD, and then we have this Gauss-Hocking Q and later one Gauss-Hocking Q Siebert or Gauss-Siebert, a different combination of the author. They have this construction of the mirror. And then on the other hand, we start with this rational elliptic surface. And then there's this Floer theory, family for mirror construction. And then with Notion, what we do is we just basically translate everything from this Gauss-Hocking Q Siebert setup to the family for mirror, and then we show that we construct this family for mirror for this two type DP5 and DP6. And from my understanding, this is the very first explicit example being calculated in terms of this family for theory construction. And that is the end of the first part of my talk. Thank you.
Thank you. Any questions?
That must be too clear.
Yeah. If no one wants to ask questions.
I'll ask a question. Is this
You are helping me to answer? Okay, where are you?
I mean, this question might be better asked later, but is it dependent on this? As you say, DP6 is for B2. Is it dependent on the choice of compactification, or is it just the fact? Are you saying DP6 just because B2 happens to have a compactification? As
Okay. At the end, the mirror we construct, family for mirror, we just have the affine piece as well. So it is the affine piece that has a compactification to DP6. Okay. And yes, the compactification will depend on the polytope we have. So we are just saying it has a compactification.
Any other questions? I can also turn the recording off. That makes people more comfortable asking.
Okay, maybe. Let me slowly start. Thank you very much for staying for the second half of the talk. That being in tiny cluster doesn't scare you. Nothing about mirror symmetry doesn't scare you away. Still, let me emphasize that this is a joint work collaborating with Fusion in Boston University, which we explicitly compute the family form mirror. And as at the end of the first talk, what we are doing is we just basically we do the Gross-Hawking Q0 mirror construction in a family form mirror construction setup, and then we have the space, and then we show that they are the same as the Gross-Hawking Q0 like mirror. And in the case of DP6, they are, because like here you're going to see me start with this rational elliptic surface. We're going to see in the case of DP5 is even by holomorphic the space we start with. So it simplified a very simplified description of the Gross-Hawking Q0 Gauss-Seibert mirror construction. You can see I even emphasize simplified in Len 2, which we start with a local pair, whereas in Julia's talk exists as smooth, compact, projective surface. And we look at the anti-canonical divisor, which is a train of projective line that in the immersion, we can think in the DP5 is this -1 curve. And actually DP6, maybe I should have drawn, is like -1, -2, -1, -2 divisor. And then here, everything I said high in Mark's talk already and Julia's talk, I'm just kind of reproducing it. And in Mark's talk, he's like having this B, the cone. The way I'm going to say it is from this local pair, we can construct this affine integral affine manifold with singularity. In Mark's talk in the morning, he'll say this is the origin. And then actually the construction here is you sort of pretending it is toric. And then, well, if you have the Toric model, you draw the dual intersect. You're not pretending that you are drawing the dual intersection complex, and then you obtain this integral affine manifold. And then in Mark's talk, he say B is the union of cone. Here I just say it's another data from this D. Then you have this cone here in the construction. And then here, as I said, at the end of the first part of the talk, in the cluster world, it's just M, which my singularity is at infinity. But like in Mark's talk, in Julia's talk, the singularity is origin. So this is an affine manifold, not the whole. I cannot say it is Rn because there's some monoidromy, there's some affine structure there. Like I say, we just do 2 examples. So example, DP5, change of 5 -1 curve. The cone will be constructed like this. You construct the cone by the toric relation. And then at the end, you should, like you have this way here. The cone should be like that. But this is the way we start with. And so this is how the monoidromy comes in. We'll write down the monoidromy explicit later. But the way is we just like kind of glue this cone out in this affine structure, and this is the affine integral affine manifold. And then again, it's getting diagram. And like in Julia's talk, Mark had mentioned that too, I forget. We have canonicals getting diagram again and again. We have the wall with rational slope. We here, the rational slope here. And then we have the function is like this polynomial or series associating to this direction. And as indicated in Mark's talk and Julia's talk, we take a lot of it. Later we'll see we'll kind of take a lot of it, but I'm not explicitly telling you the definition anyway. So I just exponential it. And this AK here encoding the counting. I remember I written down what Mark said in the first part of the talk. Okay, this is the number of curve of class meeting the boundary at one point with the contact invariant anyway. It's some counting of curve that appear in Mark's talk, and that with some finiteness consistent condition. And then Gotokin Q Siebert show that, or the upcoming Siebert paper will show that the canonical scattering diagram is consistent. But here it's just dimension 2, so it is in the Gotokin Q paper. There's many ways to describe consistent. Today we are just going of torus. So consistent to me is just simply saying the going of torus is well defined. And then DP5 is this picture, and that as in Mark's talk, we might add more wall, but in this DP5 case, the counting of curve give us at the end, we still only have this 5 walls, and the associated function are like that. And you can see the difference. Oh, sorry, this is X but not Y. Oh, I flip X and Y. Anyway, here you can see I don't have inverse here. Like this is like moving the singularity from infinity to the origin, because in the Castor world, this one line will associate to one function here. And then I have the same thing doing in the first part of the talk. What I did is I associate each maximum cone with a torus, and then I glue it by the wall function. It's basically the same thing, other than now in this canonical scattering diagram, I turn my underlying base to be of affine manifold instead of just the MR or NR. And then the next thing to do is to each integral, in this integral affine manifold, I associate a theta function to it. And again, like in Julia's talk, you can define a Buchanite. But again, because like we are in finite case, you can just define the theta function as long as you move along each torus chart, the theta function is well defined, and that is basically you can see it's kind of a generalization of toric mononomial. And then we still look at this space that is generated by theta function, like Gotokin Q Siebert, that they have an algebra structure, and the heuristic mirror that proposed by Gotokin Q Siebert is the mirror is coming from the spec of this algebra, and this is the mirror construction. So again, in the first part of the talk, we have mentioned that already, but let's do it again, which is we look at the generator. In this one too, we look at the generator of the wall, and then we look at the theta function that defined on the wall. And you can see here the reason I was saying simplified version in the mirror construction is in both Mark and Julia's talk, they have something called curve cast as a parameter, which you don't see it in my construction because I just put that term into one. And then you can see you can calculate the theta function carry this multiplication structure that they have the same polar structure. So here I can see that because we calculate in the first part that DP5, it is coming from the algebra of theta function with this relation. And here, even though we have changed a bit in our scattering diagram, but the algebra structure is still the same. So you can see this is still just giving us a DP5 in this canonical scattering diagram setup here. So that's it. And then now we move to family 4 mirror construction that is proposed by Fukaya. And I also show that this family 4 mirror functor will induce homological mirror symmetry. So this is why we want to do it or care about it, because when we have this construction, we will have this homological mirror symmetry by opposite. And in this paper, our construction is based on the construction described by Elbosai and two. We basically look into that paper and check that construction. And the motto is, at least from my point of view, like I say, in the first part of the talk, that's two take-home message. The first take-home message is screwing of torus. the second take-home message is theta function. So we just interpret everything we said in the first talk or the first two talks of today in this family for mirror construction. So here in the synthetic world, we start with a synthetic manifold with a Kähler form, and we have a Lagrangian variation. And then here, that is for each bond in the base, we can associate a Lagrangian to it. That is the picture that Mark was showing us in the morning or in the afternoon, depending on time zone. And what Fukaya Ono show is there exists an A infinite structure on the cohomology on those fiber, which is described like that, which if people know about it, they know about it, but from my point of view, I don't know too much about it. So I just quickly write about the motivation of how I can see it, which is this A infinity structure is the generalization of differential graded algebra, which you have the algebra with the grading, which I can define M1 bar, M2 bar like that. And then one can do the composition between this M1 and M2, and then we can see M1 squared is 0, and then we have all this relation there. And those are the relation that MK should satisfy. But at the end, I just want to say there exists a infinite structure on this cohomology group. And then the next thing we are in the synthetic world is something called the Maria-Cartan space. You can see I have all those little bubbles, which is what I'm thinking in our mind when I'm telling you all those notation, which are the solution of those of the Maria-Cartan's equation. But you can also see we have those MK, those are the solution there. And then in this case, we are actually having this Maria-Cartan space. It's just one. And here we are looking at, as in Mark's talk, you are going to see later when we are talking about the BP S2A2, we are looking at the Maslov index 0, this. And here you can see why I'm having a torus there, because you can see this one, if I more out C and I exponential it, I'm thinking like this is basically a torus in my mind in a certain sense, heuristically. So I have a torus. The next thing I want to talk about is schooling. So the schooling we are talking about Maria-Cartan space associated to the base, to a point in the base, which this is the picture in Mark's talk. We have the base, we have 2 points, and we want to travel along the homomorphic disk, which FOOO show that there's a isotopy of A infinite structure between the cohomology group, which induces we have a change of the algebra structure in terms of this Maria-Cartan space. That this is like some changes in our, like some wall crossing that we are having. So you can see, you can imagine that what we are doing in the family formula is defined to be the exponential of Maria-Cartan space. Like I say, you can kind of heuristically see this is basically a torus already. And if there's a change of holomorphic disk, the infinite structure, we have a wall crossing. So like a very synthetic way to see is something like that. But in this Gross-Hawking Q serial language, you can see, at least to me, is growing of torus under some map, some bidirectional map you see. And the reason to define in this way is the SYC mirror heuristic is the mirror is a dual torus fibration. So this one, you can see this one is basically what we are having here. So so here let's just talk more about the wall, which is for Calabi-Yau surface. Again, here I have 2 points in the base. When I move along, we look at the locus of Lagrangian torus binding holomorphic disk. And that here we can explicitly describe the change of A infinity structure. You can see this one. This function is precisely the wall crossing function described in the first 2 talks today. where again we have the log of the function can be expressed as the series or sum of the monomial term with some coefficient here, which we are going to see they are just some open Gamow written invariant. Yeah, they're just, this number here are just counting holomorphic disk in the homology in the Lagrangian. And so now here is kind of like a more general setup. So let us start with telling you how the space I look like. I start with a rational elliptic surface with singular configuration 2 star 2. This is the one we are going to see. The mirror is DP5. And for the case of DP6, the singular configuration would be 3 star 3. And if you like things to be more explicit, you can go to the Tate algebra, because like coming from this singular 2 star 2, you can calculate the delta, and then one can calculate how this surface can be described by the equation like that. And then here you can see again, you can do all the computation in Tate algorithm or like all the standard computation. Then you can check that here from this equation here, this is a elliptic fibration, and when t is 0 is a clip singular fiber. When this is not 0, we have nodal singular fiber here. But here the thing you can see is this is fiber over C, but we want to switch our base to be fiber over R. So we have hyperkilo rotation from this space we start with, and then we rotate it to this xt, but then we have this special Lagrangian over R2, which the space are basically the same. The hyperkilo rotation here are just switching the underlying kiloform and volume form. And then here we can define the central charge with respect to the volume form here. And then here let us redefine that our wall is the BPS rate that dictate the change of dictate the change of the holomorphic disk. But what here you can see this is a wall, is this actually lies inside the locus that is drawn by this central charge, which then we can see those are the affine, because you can see here, at least from my understanding in terms of symplectic geometry, it is not very clear that if this BPS rate is an affine line or not. It is very clear from scattering diagram point of view, sort of, but it is not very clear that if this is affine or not. And so there is this lemma showing that if I have the Lagrangian bounded a holomorphic disk, and then we have this BPS rate is affine. And here, this is one we mark, because in this scattering diagram, we have a choice of sign in the wall function, and we choose, even that choice of sign there, we can choose it so that the symplectic area of the holomorphic disk is increasing along gamma, which is the picture in the Mark's first talk. He was having this base B, and then he drew this holomorphic disk there. And that is dictating that picture that Mark is drawing in his very beginning of his talk. And then here, okay, here is, we have some line. You can see that this is, to me, we are reconstructing what we have in the scattering diagram. So we can talk about chambers, the wall and chamber structure there. And then here, the wall causing function, 2 pages ago, we're showing you since we saw about the change in the A infinity structure can be described by something we like wall causing. And then here we can explicitly say how the wall causing function look like, which is almost identical. Oh, I didn't know it very identical as Mark and Julia's talk, which is log of the F gamma equals to the sum of series with the coefficient is given by this open Gamow written invariant counting. But in this case of DP5, or rational elliptic surface with singularity 2 star 2, one can see explicitly the open gamma invariant are just this one when we have gamma 1, like in this case. And here we can explicitly write down our scattering diagram here, which as we mentioned, we have a homomorphism. It's not in the cluster static. We have the homomorphism in the base described in this way. And like I say here, all the walls are outgoing, which I have this choice of this direction gamma 2, the function will be 1 plus c gamma 2. And what you can see is a bit interesting that I wrote gamma 1 here, gamma 2 here. The reason is actually Yushin and there's many identification behind we are doing here. This is actually we are computing both the complex and the synthetic structure of the affine coordinate, and this is the synthetic affine coordinate structure. So the x is here, but not in the usual way is there. So this is what we have. And so you can see we are pretty much ready. We have a scattering diagram, we have everything. We can start with the synthetic world to define it. So at the end, we just want to associate a chamber with a torus, and then we glue it. So you can see I just like roughly say I associate each chamber with a torus, and then I glue it by wall crossing function. And here we have our canonical scattering diagram. It's consistent, so the gluing is well defined here. But I just want to say, you can see I have been very careful putting co and co in in what I draw. The reason here is actually, like, because here we move to the synthetic static, our underlying base ring is no longer C, but no confused. So when we take the spec, we are looking at the rational domain. It's actually when we look at the spec, the rational domain is very small. It's just a unit disk. So so actually there's some construction there. We extend this UI to be the like cover almost everything other than something cool I mentioned too in this analytic torus. Because here you can see I put a and there is no longer C star square. It is the torus in this Tate associated to this Tate algebra there. And then but at the end, once we finish all the construction, and then we can define this family formula as the gluing of 5 analytic torus, which in some sense we don't need to do anything. The reason is we have in the Gauss-Hawking Q consideration, Gauss-Hawking Q Gauss-Seibert setup that we know that, forget what I have here, we have gluing of 5 torus, we know it's dp5 already, and all the gluing functions are algebraic, they are just polynomial with finite term. So by Gaga's identification, we can just leave up all the gluing to the analytic setting. So here we can have the analytic gluing of 5 analytic torus. And so here, well, you can see I basically get anything already, but at the end, I still want to know how the space looks like. It doesn't matter that much to look at dp5. So dp6, if we want to identify this as dp6, we still want something like theta function, but we can define as almost analogous because the same way as in the JHK world. And then we check the algebra structure, and as long as we do that, we got the same product relation as I keep on repeating, and also the one up here in Julia's talk as well. So we know that our space, as Mark have pointed out at the end in the Q&A session, we get a space that carry a compactification to dp5. So with Yushin, we start with this rational elliptic surface with singularity 2 star 2 or 3 star 3, and then the family formula of this space can be compactified to dp5 or dp6 in the second example. And then we are not only, you can see as I keep on describing, it's not only the construction, but what we do is we basically identify all the notion in the Gauss-Hocking Q, Seibert mirror construction in the family formula theory, that we interpret anything we give them, not heuristically, but explicitly show that there is this correspondence there. And then we show this family formula construction. And I forgot when I start, but it seems like I end a bit earlier, but I hope it's okay. And thank you very much. That's the end of my talk.
Thank you very much. So any questions?
Mandy, if you just go back to that table you just showed, so go back one page.
You're the person who helped me answering questions. Well, anyway.
This is just for the DP5, DP6 example.
Yes. But actually, what we believe is we'll get D2, G2 case, which should be DP4. And I don't know, actually, when we are doing the computation, it appears that we can extend it to more general cases, at least for diamond 2. But this is something, DP5, DP6 is something that we are very definite. That's why I'm saying that here. But there might be a chance that we can extend it to more general cases.
I mean, I guess this answers, at least in these examples, the question that someone asked me about to what extent could the scattering diagrams be really interpreted in terms of the original mass sum index gene discounts.
I want to say that too, but I was too embarrassed, so I was like, you know better. So.
Well, I mean, yeah, this is the first time I've heard these results of yours. So,
yeah, but at least DP5, DP6, this A2 and B2 case, we are very definite. We literally compute everything.
Thanks.
See you.
In the third line of this table on the left, when you say loci of XYZ fibers,
that is what I mean by the BPS way.
When you say loci fibers bounding holomorphic disks, what Maslov index do they have?
Maslov index 0.
Okay.
Yeah, it is as in Mark's talk as he indicated in the morning.
Other questions?
Maybe I could ask a question of maybe both to Mark and you, because I'm trying to understand some connection. If Mark is still also here, are you? Okay, so I'm trying to understand where the passage of Boguscon occurs, namely. So while we were discussing with you when we write a mirror to DP5, which is over the Moricon, do you remember with Tom Coates and you, we were discussing to the passage to the Boguscons, Shankil and Tony Yu define by changing the Moricon to, if you have a toric model given by a blown down map F, we take to X bar, we essentially take the K-lacon and F exceptional devices, which Tony Yu and Shankil call the Boguscons. So when making this change from the Moricon to the Boguscons, we wrote down the families of the Boguscons and we did compute partial compactifications and obtained DP5 actually. So when we wrote the families over the Boguscons and when setting up some variables to be 0, they gave algebraic geometric methods to obtain compactifications. I was just curious when Mandy said they Floer theoretically obtained this compactification DP5. Is there some similar passage from changing from the Moricon to some other generating set of cones? Do you have an idea?
So if I can answer that question, I think my question to Mandy earlier was they didn't actually get the compactification, rather they were just getting open piece.
I see, but they could get the compactifications by choosing specific toric models like we described. I mean, Mandy told that there's a compactification to DP5, so I was curious.
Yeah, I should let Mandy answer the question.
I don't know. Is it a bit too long? Okay, like I say, I see everything from the caster point of view. So to me, the compactification comes from something I mentioned is the positive polytope, which to me is a generalization or analogy from the Toric picture. Yeah, maybe that will be another talk, which is the projective Toric variety is defined by a convex polytope, and then you put it on layer 1, and then the cone over it, and then we have a graded ring, and then the pouch of the graded ring will be a projective Toric variety. So positive polytope is the same thing, but then the grading will be we switch the Toric monomial to be theta function, and then that the positive polytope will give me the positive polytope will give me a grading to the algebra of theta function, and that I can take a pouch of it, and that is how I see I get a compactification, which like DP5 is pretty much calculated in GK already, but DP6 you can see I can obtain this polytope in the first part of my talk, which carries 6 index. And then I calculate the Porter structure, which is on degenerate. And then, because this DP theory is embedding to K of degree, that is degree K. So I know that is DP6. So, but like my point out, the thing is like I say, I'm not that used to your language. To me, it's the caster language. The positive polytope is not unique. Like there might be more than there's some other choice of the positive polytope in the scattering diagram of type B2 or other type caster. So there might be other compactification as well. But you can see here this construction, I'm just going towards whatever sense, analytic sense or contrast towards. So they are the open part. So like I can the thing is this schooling will work anyway, but the thing it would be nice, at least to me, that I can tell people, oh, this is DP6. So, but like Mark Hornell, it's just a compactification of the construction. I don't know if that answers your question.
Yeah, sure. I think there's some translation of language between your choices of positive polytopes and what we were discussing with Shankil and Tony Yu's choices of bogus cones. But I think it became clearer. Thank you. It reminds me a second last question of the Slapakeda rotation you were talking of. It reminded me many years ago, Mark, some person at Mass Overflow asked, is mirror symmetry like hyperkähler rotation in relation to K3 surfaces? I think the topic was mirror symmetry and hyperkähler rotation, and you were having very strong opinions objecting. Do you remember that?
Oh, is this the, maybe I shouldn't say things publicly, but are you from this old physics paper claiming hyperkähler rotation was mirror symmetry?
Yeah.
Yeah, I had strong opinions.
I think something on Mass Overflow.
Have you stopped the recording yet? Or?
Oh, yeah, I actually have a question. Like Mark pointed out that this table doesn't work like in general, but like, so what would be like a next example you would try to achieve this?
P2? It will be DP4. That is what Yushan and I are doing. I don't know, Mark might be doing something else. You get doing something higher than
what are the expectations like?
Maybe let me comment on there's my work with Xuchuan and Zhongru Li. So we proved that for the case of say P2 throw away an smooth anti-cone divisor, then Tristan, Adam, and I will construct a spatial Lagrangian vibration on it, and then with Suchong and Zhongru, we proved that the complex defined structure of SYZB is exactly the one that constructed in the work of Carl, Pampola, and Zieber. And so, so in this case that we have this, and then I have another paper that carry out the rest of the correspondence completely. And so like in this case that, say in the case of P2, you can have a lot of interesting applications like the counting of holomorphic disk of Maslov index 0. If they're in the right direction, they are exactly corresponding to all those like counting of A1 curves. And so, yeah. And also like comment to Mark's earlier comments, like for relation of hyperkähler rotation, that maybe like let me advertise Tristan's talk tomorrow that also there is some weird relation between mirror symmetry and hyperkähler rotation. It's not, I don't know why, but there's still some relation, although it's not clear why that happens.
Any other questions before I turn the recording off? Okay.
So you will be in dimension 2 though if you do this hyperkähler rotation thing. So is there any hope you can relate higher dimensional things, higher dimensional canonical scattering diagrams to family Floer mirrors? Maybe.
Yeah, I was thinking the same thing.
Mandy?
Are you asking me?
Or you, Shani, I don't know. I was just
Okay, yes, we are thinking high dimension too. But I feel the next thing is to do the unit case in LAN 2. And my feeling from, because, okay, you know, it's kind of depending on Yushan's work. That's why it's a collaboration with Yushan. Like, it's all those holomorphic discounting that is being calculated or not, right? Because our calculation lies on, we have the wall crossing are really given by those holomorphic discounting. Like, my feeling is as long as we got all that, then it should hold in general. Yeah, because the construction will basically. Yeah, but I guess, but yeah, you guys are working with canonical scattering diagram. My understanding is still the same thing, right? You push the singularity, like origin to infinity or the other way, then you can turn into cluster. Like my point is, as long as you give me a cluster scattering diagram, and then I can give you all the relation, then we can start talking about the relation, because they are just cluster mutation from my point of view. But like I say, even for when Yushan and I, we are calculating, our feeling is this is our computation is very general, so we haven't write in a way that it sounds very general. Like I'm more on the conservative side. Like this is something we definitely have now, so.
thank you.
Other questions? Maybe I'll turn off the recording.